Hi everyone, my name is Justin Croft and I'm the Vice President of Optronix North America. At Optronix, we help researchers measure what's happening in living tissues, especially in studies where oxygen delivery and microvascular function are central to the biology. Much of that support ends up in cerebral research areas like stroke, trauma, neurovascular coupling, and brain metabolism. In this space, small changes in perfusion and oxygenation can completely change what a result means, and that's really where this webinar stems from. So today, I'll keep it practical, and I want to leave you with a clear sense of what flow tells you, what oxygen tells you, why they sometimes disagree, and how that helps you interpret a real data set. Let's start with blood flow, because that's the delivery side of the story. So when we talk about cerebral blood flow, the main point is that neurons don't have much of a buffer. Continuous perfusion in this case is a non-negotiable. Flow is how oxygen and glucose get in and how carbon dioxide and metabolic waste get cleared out. And the reason this slide matters is the last line. You can have a big vessel that looks fine while the microvascular bed is struggling. In preclinical models, this is one of the most common ways people get surprised by their data. Okay, so now that flow's on the table, let's talk about oxygen, because that's the tissue level reality check. So what does tissue oxygen add? Even at rest, the brain uses a disproportionate amount of the body's oxygen, and it does not tolerate interruptions well. Tissue PO₂ is useful because it reflects the local balance between delivery and consumption right where the biology is happening. Now, if we take a look at the timeline graphic here, it's the motivation for this whole talk. A few minutes without oxygen starts creating real risk, and after about 5 minutes, the danger of severe injury climbs quickly. So if oxygen can swing fast, it's worth measuring it directly instead of trying to infer it later. So here's the key question. If flow delivers oxygen, do they always move together? And the answer is not reliably. Flow brings oxygen, but it's not a one-to-one relationship. Tissue PO₂ depends on delivery, of course, but it also depends on extraction, diffusion distance, capillary recruitment, hemoglobin dynamics, and metabolic demand. So you can see flow improving while PO₂ barely moves, or PO₂ dropping without a dramatic flow change. That is not a bad measurement, that's often the biology. The simple way to think about it is, flow is a delivery truck, and PO₂ tells you what actually made it to tissue and stayed there long enough to matter. Once you accept that decoupling can happen, the next step is choosing measurements that help you explain why. This is just my friendly scientific bias, but I always choose mechanism over assumptions. Without oxygen and perfusion, injury progression or treatment effects can become a real black box. You see an endpoint, but you're guessing what happened in the minutes and hours leading up to that point and what actually mattered. And I like the last point here because it gives you permission to be curious. When flow and oxygen diverge, that's not just noise. It's often a clue that tells you what to test next. With that framework, let's look at what shows up in real research areas, starting with stroke. In stroke, core versus penumbra is really about what is still perfused enough to be salvageable. Collateral flow can often look reassuring, but it doesn't always mean the tissue is actually being rescued at the oxygen level. So real-time flow and oxygen monitoring can help you answer a few practical questions. Did our intervention improve delivery? Did it improve tissue oxygenation? And did that improvement actually hold through the window that matters? Trauma is another place where these signals earn their keep, especially because physiology can be episodic. With TBI, much of the injury isn't actually the first hit. It's what happens after over minutes to hours. Secondary events can drive signatures in flow and oxygen that you'd never catch with a single snapshot. And if you've ever had a study where behavior worsened later and you weren't sure why, this can often be the missing link. Longitudinal physiology helps you see whether there were repeated insults along the way that may help explain an endpoint. Now, stepping away from injury, let's look at a more normal brain function, neurovascular coupling. In neurovascular coupling, the key idea is that when neurons get busy, the microvasculature responds. Flow response to stimulation is measurable, and oxygen tells you whether the delivery actually matches that demand. And I really like this activated versus resting illustration because it's intuitive. When neurons get busy, you expect flow to respond and you want oxygen to keep up. If those relationships shift under anesthesia, CO2 changes, or inflammation, measuring both helps you interpret what you're seeing. This naturally connects to imaging because a lot of imaging is oxygen sensitive, but still indirect. So with imaging, the big caution is that many signals are not oxygen by default. This tumor example is a good illustration of this. Under some conditions, MRI and probe measurements line up perfectly. Under others, like in the carbogen example, they separate, largely because tissue response is heterogeneous. And the MRI in this case is averaging over voxels, while sensor samples are measuring in a much smaller local region. So the practical takeaway isn't that one is right and one is wrong. It's that physiology is not uniform, and direct PO₂ or flow helps anchor what the imaging signals actually represent. Okay, with that context, let's take a quick look at the signals and what each system tells you in practice. So here's the Oxford Optronix systems I'd like to talk about today. This is our OxyLite and OxyFlo. The OxyLite, which is the blue system, gives you absolute tissue PO₂ in millimeters of mercury with optional temperature functionality. The practical question it answers are things like, is this tissue actually oxygenated enough? And how does that change over time? The OxyFlo, or the red system, gives you microvascular perfusion using laser Doppler. It answers, is local perfusion changing? And when does it change? And it's worth saying this out loud. Either metric on its own can be very strong. Lots of great studies use only oxygen or only flow. Having both just gives you more leverage when you're trying to explain a mechanism. So next, let's talk about how you collect these signals cleanly and why probe choice and co-localization matters. Okay, so this is the same spot argument. When you record flow and oxygen from the same microregion, interpretation gets cleaner because brain tissue is heterogeneous and small spatial offsets can change the story. So again, you can absolutely run OxyLite and OxyFlo independently, but when you're trying to separate delivery from extraction and demand, co-localization is a big deal. And for longitudinal work, chronic implantable PO₂ approaches are an option too, especially for awake recordings over time. Finally, because these fiber optic measurements, there are practical MRI-friendly workflows too, depending on the study design. Okay, so with that foundation, let's jump into a few case studies and look at real data sets. Okay, so here's the first example. This is an ovine brain injury model during experimental extracorporeal support. Here, they use continuous neuromonitoring that includes laser Doppler flow and brain tissue oxygen tension. On this slide, I want you to focus on the trace below. This group compares low flow versus high flow, and the separation between the groups is really clear. And the simple takeaway is in a vulnerable brain, blood delivery to a tissue can diverge dramatically depending on the support strategy. And that divergence happens on a timescale that matters in an experiment. Now let's add the oxygen layer because that's where we can see what the brain actually gets. So this next figure adds the tissue oxygen beside the flow metric, which better shows what the tissue is actually experiencing. So here we can see that PO₂ alongside flow, and clearly tissue oxygen is substantially higher in the high flow condition compared to the low flow. And this is exactly why pairing these metrics is helpful. Flow tells you the delivery capacity, but tissue oxygen tells you what the tissue is actually experiencing after diffusion limits, heterogeneity, and demand are all in play. Okay, so now that we've seen this in a larger animal model, let's stay in brain injury, but shift to a different question. What happens when seizures enter the picture after a mild TBI? So this next case study is a repetitive mild TBI, concussion-style injury, and the question is whether some animals enter a state that helps explain post-concussive defects. The team here recorded hippocampal EEG and tissue PO₂ in awake, freely moving rats. Some animals show electrographic seizures right after impact, even without obvious convulsions. And what you can see here is that the seizure group follows a distinct oxygen trajectory that is much higher compared to the non-seizure group. They also were able to define hyperoxia as greater than 30 millimeters of mercury, which helps anchor interpretation. So this slide is the setup, and the next slide is whether they test whether the oxygen piece is just a passenger or actually part of the mechanism. Okay, so here's the key figure because this really is their mechanism test. So the team tests BK8644, which in plain terms makes calcium channels more likely to stay open, so more calcium can enter cells when they depolarize. In this study, it's used specifically to blunt the post-injury hyperoxia after injury in animals with prior seizure history. As we can see, without the drug, the oxygen trace pushes well above the hyperoxic threshold. But with BK8644, the trace returns towards the baseline and stays much closer to the normoxic zone. That really does shift the story from interesting association to actual outcome. The BK8644 group ends up statistically indistinguishable from sham or no seizure animals on the behavior measurements they report. Okay, so with that, let's jump to stroke, where PO₂ gives a clean readout of delivery changes in threatened tissue. Okay, so in stroke, the question is often, did we actually improve delivery in a way that supports threatened tissues? In this example, the team measured brain tissue oxygen continuously and used it as a direct physiological readout of delivery changes. Now, this is also a good reminder that oxygen alone, when measured well and continuously, can be a very strong metric, especially when you're trying to show that something improved conditions in tissues that are at risk. So here's the clean result from this team's stroke models. After Exendin-4 was added compared to a saline control, cortical oxygen increased from roughly the low 20s to around 30 millimeters of mercury. And just as importantly, this effect persisted over time. And this is what continuous monitoring is great at. You see an onset, a magnitude, and whether a response was transient or sustained. And again, even though our broader theme is oxygen plus flow together, this is a great example of how tissue oxygen alone can support a mechanistic story about improved delivery. Now, let's connect back to imaging, because a lot of imaging is oxygen sensitive, but still indirect. When researchers say oxygen in imaging, what they often mean is an oxygen sensitive signal, and that's not exactly the same thing as tissue PO₂. Bold and related MRI signals reflect deoxyhemoglobin effects, so they're shaped by flow, blood volume, and oxygen extraction fractions. That's why tissue PO₂ measurements with imaging studies can be so helpful. They provide you an anchor so you're not forced to infer physiology from an indirect signal. The next example shows what this looks like when you explicitly link MRI metrics to tissue oxygen. So this fetal sheep study is a great example of that validation mindset. Here, a team combined MRI oxygen sensitive metric with direct brain tissue oxygen tension measurements. And they show that MRI changes track oxygen dynamics during controlled hypoxia. So instead of saying this MRI signal must mean oxygen, they build a bridge between the imaging metric and the measured PO₂, which makes the imaging conclusion much easier to defend. And it's also a nice reminder that these approaches aren't competing. Imaging gives spatial context, and direct PO₂ gives you ground truth to rely on. All right, We've seen flow only, oxygen only, and combined examples, so let's make the framework a bit more explicit. And finally, this is the how to interpret what you just saw slide. So the OxyLite on its own gives you tissue PO2 in millimeters of mercury and provides a direct readout of local oxygen availability. It's excellent for capturing hypoxia and hyperoxic episodes and for longitudinal physiology. And as you saw in the TBI and seizure study, continuous oxygen alone can be enough to uncover mechanism-relevant physiology. Moving on, the OxyFlo on its own gives you microvascular perfusion dynamics with laser Doppler. It's great for seeing instability, drops and rebounds, and coupling or uncoupling with demand. And together, from the same microregion via a combined PO2 flow sensor, you can separate delivery effects from extraction and demand effects when signals don't match. That reduces spatial confounds and makes the mechanistic story cleaner. Why did oxygen change, or why didn't it? So to wrap this up today, flow and oxygen answer very different questions. Measuring either one well and continuously is absolutely valuable, but measuring both together, especially from the same microregion, can really strengthen the conclusions you are trying to defend in your preclinical brain work. If you are planning cerebral monitoring research and want to sanity check your approach, we always offer initial and ongoing application support for free. These systems have been well cited, well over 750 times, and we have team members with 20 plus years of cerebral monitoring experience who can help you with sensor choice, placement, and workflows for reproducible data. At Oxford Optronix, we're always happy to discuss any application, recommend a setup, and support you fully through getting high quality, reproducible data. Thank you again for your time and have a great rest of your day.